Hi everybody. I'd like to welcome everyone to our first colloquium of 2016. Brian's he's teaching and knew that class was going to run long, so he asked me to introduce our speaker and friend of the department, Flavia, who has come back to Wittenberg. For those of you that don't know, Flavia was taught here from 2011 to 2014, and some people here are old enough to have had her in class who had Flavia. There we go. A couple of them. And so we're very happy to have Flavia back. Flavia moved on to Antioch University just down in Yellow Springs, and so she's not too far away. Her husband, Dave, works at Sinclair. Sinclair. And they have a little all-American dog, Peppy, that they hang out with down in Yellow Springs. And so join me in welcoming Flavia back to Wittenberg, and I know a lot of you are excited to see her.
How's everyone doing? Good. So today's talk, let's make sure you can see it. So I'm going to talk about a game called Risk. Just as a survey, can I have a show of hands for who has heard of the game Risk before? Okay, everyone. Can I have a show of hands for who knows how to play the game? So we have maybe a couple that don't. So I'm going to go quickly over quickly over the rules of the game, just to make sure that everyone is on board. And by the way, so the title of the talk is Risk and War. Is a good offense the best offense? And War is another risk-type game, and I'm going to make clear what the little difference is in a moment. But that's the version that we play in Brazil, and I'm from Brazil. And so I grew up playing a War instead of Risk. I actually only knew of the existence of the game Risk when I came here. And I was like, oh, they're totally copying that game that I played. And it was actually the other way around. So Risk has been... Oh, okay, we're going to have to go like this. So the first version of Risk, I think, was a French person that came up with, 1957, so it's that old. And War, which is the variant that was released in Brazil, is from 1972, so quite a bit older, newer. And so just before we go over the rules, I just want to show you the map real quick. Okay, so, there are many maps out there nowadays. So this is one possible map. There are 42 countries divided into 6 continents. And this would be the beginning of a game of War or Risk. They're very similar. And here we have 6 players. Each color represents a player. And so in the beginning, everybody has one army. So each, you see a number 1 on everything, meaning that everybody has a number 1, except that the first player has already distributed its first round of armies. So you would receive 3 armies in the beginning, and then as you conquer more territories, you may receive more. So for example, in Risk, I believe you divide by 3 the number of territories, and that's how many armies you can put, but 3 is the very minimum that you are allowed to have. In War is a little different. You divide by 2 instead of 3. And the reason for that is because it'll be clear in a little bit when you're attacking in War versus Risk, the defense has the advantage, and so you're allowed to gain more armies as you go. So for example, this would be the first round, and then next is the green one. So the green one chose to put its 3 armies over here. And so you keep going, everybody's distributing their first round. Right, the red chose Borneo. Right, and then when it goes back to yellow, then yellow is going to choose now to attack. And yellow attacked Colombia, etc. So, and the game goes on. Now let's go over some of the rules. So the game is played on a board divided into 42 territories. And the objective of Risk is to conquer all territories. Right? So you gotta be kind of strong enough that you can conquer the world. The objective of war is very specific to each player. So for example, a player may draw an objective which is to conquer Asia and Africa. The other player may have an objective which is to conquer North America and Australia. Right? So objectives vary. And the reason for that is because the game moves much slower. In order to conquer more territories, it takes a lot longer. So each player is given a number of tokens, armies, determined by the beginning of each turn, right, depending on how many armies you have. And on each turn, a player may attack an adjoining territory controlled by a defender. Right? So on that map, you can choose any of your neighboring countries to attack. And if you win the battle, you conquer that territory. And then it keeps going like that. The attacker must have at least 2 armies in order to attack. Because the attacker, let's say you have to have at least 2 armies, because if you lose one, you can still occupy that territory. Okay, so when you're attacking, you can never lose that territory that you're attacking. Only the defender can lose that territory. And an attacker may choose to withdraw from war at any time, but if they remain in battle until the end, there are 2 possible outcomes. The attacker ends up with 1 army, didn't conquer a territory, right? So it just kept on losing armies until it had 1 left, so it didn't conquer that territory. Another possibility is that the defender ends up with 0 armies, which means the attacker managed to conquer that territory. So far, so good? Now, here are the rules that pertain to this topic. So in order to determine if a battle is won or lost, both the attacker and the defender roll dice. So this is where the chance comes into the game. So the attacker will roll no more than 3 dice. It'll roll less if it has less than 4 armies. So the idea goes like this. Let's say an attacker has 3 armies. Okay, so this is the attack. Now this is the defense. So let's say this is the scenario that we have. We have 3 armies against 2. So the attacker, one of the armies for the attacker has to be the occupying army. So you're not allowed to use that for attacking. So the attacker is going to roll 2 dice, and the defender is going to roll 2 dice. So the defender can roll the number of dice corresponding to the number of armies that they have, except that the defender can only roll at most 2 dice. So if the defender had 3 instead, it's still going to roll 2 dice. The attacker, on the other hand, can roll up to 3 dice. So if we had an additional 1 here, the attacker would roll 3 dice. Okay? Now, once the dice are rolled, they are placed in descending order. And the attacker's highest die is compared to the defender's highest die, and so on. So for example, let's say the attacker rolled 3 dice. So you would place them in descending order. So let's say this could be number 5, number 4, and number 4 again. Right, so this would be a possible throw for the attack. And then the defense would throw 2 dice, and you would do the same thing. You would order the defense in descending order. And let's say this is a 3, and let's say this is a 3 again. So what we have here, in order to decide, who loses what and who gains what, we would compare the highest number from the attack with the highest number from the defense. So 5 against a 3, 5 wins. Can we do this a little differently? Let's make this a 4. So 5 against a 4, 5 wins, and then I'm going to do a 4 against, that's not what I meant, but okay. So when you do a 4 against, I wanted to show what happens on tie. So what happens in tie? The fence wins. Yeah, so the fence wins, right? So for example, if we had, just for the sake of an example, so if we had, now comparing a 4 with a 4, then the defense would win this one, and we would end up with, so this particular attack would end up with the attack loses 1, and then the defense loses 1. Okay, so from here we can start to realize what are all the possibilities when you have one such attack. Right? We know now that attack could possibly lose 1, could possibly lose 2, right? Possibly lose 0, and the same thing for the defense. So we have all these possibilities. So we'll talk about finding those probabilities of conquering territories, but first, I want to try to have us think of a way of setting this up so when we finally find these probabilities, we can in one shot find probabilities of conquering the whole territory if you have this huge attack. So for example, examples like a 4 against 3 are fairly small in terms of what are the possibilities for attacks in the game risk. What if you have an attack that is 20 versus 10, for example, right? So you start having many possibilities here for what paths you can take as you keep throwing these dice. So imagine one such throw and attack loses 1, defense loses 1, but you have 20 against 10, so you can keep on going. And so how can we find what is the probability of conquering that territory in such an attack? So what is a way that we can think of it without necessarily having to spend the next 3 months calculating that probability? Right? So we're going to go the route of setting up a Markov chain. And by the way, there are other ways in which we can estimate those probabilities. One such way would be solely through computer programming, right? You can set up a computer simulation that simulates each throw of dice, and then you can just do that 1,000 times until you finally ends up with either this 0 or this 1. So that is one such way, and I have done that, and I have spent half hour in one calculation before. When I got to 30 versus 15, or something like that. Then you end up spending a lot of time. Of course, I'm not a computer scientist, so maybe there's a better way in which I could have done that. But that's one possibility. You can go straight to the route of simulations and try to estimate those probabilities. But we'll try to do something different. How many of you are familiar with Markov chains? Okay. So don't worry, everything you need to know about Markov chains, I'm going to do my best to share with you. So a very loose way of defining a Markov chain is a mathematical model that possesses the property that the outcome of one trial depends on the trial immediately preceding that trial. So some example, this is an example, right? Let's say you engage in this battle, and at some point, after who knows what happens here, how many times you attacked each other. Let's say the scenario now is 15 against 7. So a Markov chain model says that it doesn't matter how you got here, what happens next, it only depends on where you are right now. Right? So you're looking forward, and whatever's going to happen looking forward only depends on where you are right now. So loosely, we can think of a Markov chain as being such a process. And so we'll use a Markov chain to try to answer this question. What is the probability that if you attack a territory, you will capture that territory? All right, so some notation. So we're gonna denote by xn our state on the nth attack, right? And we're going to start with A being the total number of attacking armies and D is the total number of defending armies. So we could have AN, so thinking of a scenario like this, after several attacks, you could end up with 15 versus 7 at some point. And so your AN at that moment, let's say after 5 attacks, this is what you have. And D5, after 5 attacks, this is what the defense has. So we're going to use A for attack and D for defense. And the initial state is going to be 80. You're starting with 20 the attack and 10 the defense. Now, the probability for moving from one state to the next, which in Markov processes we call that the transition probability, depends on xn, right? It only depends on where you are right now. So this is known as a Markov property, right? If that happens in your model, then that's what characterizes being Markov. And using Markov process notation, we can write that the probability of state xn plus 1 being equal to something, given that all of these things have already happened. Xn it was equal to something else, xn minus 1 was equal to something else. That probability equals the probability of xn plus 1 being equal to something, given that xn happened. So you can erase everything that happened before the present and only look at the present. The idea is that the present has all the information you need in order to move forward. Are we doing okay on that? So let's go ahead. In order to set up, the beautiful Markov process, we're going to need to order all possible states. And all possible states will depend on what is the attack that we are talking about. So we're going to use as an example A equals 3 and D equals 2. So a very small example, which is actually going to generate a model that doesn't look so small. But we're going to order it the following way, regardless of which example we're talking about. We're going to first list our transient states, and then we're going to list our absorbing states. So in a Markov chain, the transient states are the states in which you can still go from that state to something else. You're still moving around, right? So for example, this would be a transient state because when you engage in an attack, you can still move into something else. But if this is your if at some point you end up with this, then you can no longer engage on something else. Okay?
No.
The attack has one. Can the attack throw another time? No, so you're done. Right? That's called an absorbing state. Once you reach that state, you're there. There's no moving from that. And here you can still move from that. Right? So all of these are transient states. And a battle is going to be over when you reach an absorbing state, which could be something that looks like this, the attacking army has one, or it could be something that looks like this, let's say, right? The attack conquered that territory. So all of these are absorbing states, and all of these are transient states. Okay, so if we list in that manner, so when we're setting up a Markov chain, it's important that we know how to list all of the possible states. So we're going to first list the transient ones, which start with, so remember, this is the attack, and this is the defense. So if I have 2 attacking armies and 1 defense army, I can engage on an attack, right? And so this is a transient state. This is a transient state. And so it's everything up to 2D. But of course, we can also list this is a transient state, right? All the way to and we keep going all the way to A1, etc. 18. Yes? And that gives us A times D minus D states. And minus D just because we didn't list, the ones that just started with a 1. Okay? So we have a total of A times D minus D states that are transient. And then these are the absorbing states. Everything in which has an attacking army equals 1, and everything that has a defending army equals 0. All right, so let's, so what we need to do now, once we have listed those, so we're going to call this, state number 1, state number 2, etc. Right? So we're going to list all the states, and then we're going to try to define a matrix speed that denotes the probability of transitioning from state I to state B. Yes? So, so this is what our PIJ is going to be. And in Markov chains, coming up with that transition probability matrix is the first step of calculating all sorts of probabilities and probabilities of ending up in a certain type of state. And so that's what we're going to do next.
Flavia?
Yes.
Sorry to interrupt, but before you get onto the transition probabilities, but on the absorbing states, is 1, 0 a possible absorbing state, or could you never really get there from anywhere else?
No, because, thank you. Yeah, actually, thank you. I needed to make a remark about that. So why is 1, 0 not there? What's happening there? No? Yes.
I don't think that can ever occur because for there to be a 1 and a 0, then someone would have had to attack and then move armies there, right?
Mm-hmm. Yeah.
Isn't there a rule that you can't roll 1 dice?
Right.
1 die.
Right. So that would, on a game, it would never be the case that you would end up here, because you would not be able to, you would not be able to engage on anything if you were there. Does that make sense?
Is it possible to go from 2, 1 to 1, 0?
No.
If actually they're each just rolling 1 die, and then there's no way for each side to lose 1? Is that it? Okay. So that can never happen, right?
Right.
Okay.
Yeah, that's not a state that will, that will ever exist.
Okay, thanks.
So we just take that out, and that gives us that -1. Let me see that. Right.
But a zero, exactly the 0 state is a state. You can get 0 anything.
Say it again.
The absorbing states so far are attacker 1 or defender 0.
Yes.
Or attacker 0. That can actually happen. Yes.
No. So an attacker will never lose its last territory. An attacker, because if an attacker...
That's right.
Yeah.
One less. Okay.
You're correct, you're correct.
That would be that
No,
the
you got
defense
it.
is stronger in some ways. More questions? So let's check what this transition probability matrix would look like for this. There's one example, A equals 3 and Z equals 2. So I'm going to go ahead and start occupying a lot of board space. So I'm going to use this. Okay, I'm going to try my best to give you something meaningful up to 5. So we're going to, there's a lot of calculations that we could do here. So I'm going to show you, this one example and then sort of summarize what happens when we have a lot of attacking armies. So if we have attacking armies equals 3 and defense armies equal 2, let's go ahead and list all possible states. Okay, so remember that we can only, let's list the transients one first. So transients, we're going to start with 2, 1. 2, 2, can I get some help?
3, 1.
We're not going to do 2, 3, right? Not go that far. 3, 1. 3, 2. 3, 2. Cannot do 3, 3, right? Yes.
No, 3, 2 would be no one over the top.
Yeah.
3, 2.
So is that's the beginning state then that counts as a transient?
Yeah, so that's the beginning state. So that's a transient state, because from there you can still engage in an attack. Right? So we're going to list that as a transient state. So you can roll, you can engage in an attack then, and then from there it's going to move to something else.
How can you do 2, 2?
How can we get into a 2, 2? Okay, you guys are asking important questions now, because you're going to realize that you cannot necessarily achieve any of those states. So when we're constructing those transition probabilities, many of them will be 0, meaning that you cannot get from one state to that one, right? So I'm going to ask that you engage on those thoughts again when we start calculating those probabilities, right? Because you're going to see that it's not, we're going to list all the states, but sometimes going from this to something else, maybe that probability is going to be 0. Okay, so let's just list anything that could potentially be possible, and then we'll find out if the probability of getting there is 0 or not. Yes?
Can I ask some clarification about one of the rules? If an attacker has like 10 armies, are you allowed to attack with fewer dice essentially? Like you're allowed to attack with up to 3, but must you do 3? Can you say, okay, I've got 10, but I'm attacking with only 2? Yeah.
Some variations of the game allow you to make that choice, but the rules that we are using to calculate this, you would always use the maximum number of dice.
Okay.
And even on games that allow that, it has already been proven that it's always to your advantage to use the maximum number of dice. And so we're going to assume that the player is as smart as possible and is playing by this assumption. So in our rules, you're always going to throw the maximum number of dice.
Okay.
Okay, so 3, 1, 3, 2. So do we have any more transient states? Okay. So 4 transient states. And as sorting states, anything in which the attacker essentially lost the battle. So we have 1. Do we have this?
Yeah.
Do we have this? What comes next?
3 0.
3 0. Could happen, yeah. 2 1. 2 1.
2-1 the attacker.
2-0.
Yep. Now, just to be true to how we, I already moved that up, but just to be sure that we are listing in that order that we agreed with at the beginning, I'm going to list the 2 0 first. And then we're going to do, what else?
3 0.
3 0. Anything else? That's it, right? So 8 states. Okay, so what we would do next, let me use this board over here. So we're going to list, this is going to be, actually let me go ahead and write all of this again. So 2 1, 2 2, 3 1, 3 2. We have 1 1, 1 2, 2 0, 3 0. As reminder, so this is the states number 1, states number 2, etc. Right? So the 8 states. And then we're going to do the same thing. So 2 1, 2 2, 3 1, 3 2, 1 1. And so now we can fill in the matrix, right? So this is row number 1, row number 2, row number 3, etc. All the way to row number 8, column number 1, column number 2, etc. So the number that we're going to put in here is the probability of transitioning from this state to that state. Remember, we're trying to define our transition probability matrix P, where Pij is the probability of transitioning from state I to state J. Everybody with me? Okay, so we can, let's go ahead and 1, 2, 3, 4. So these are the transient states. I just want to do a reminder of this division as we calculate those probabilities. 1, 2, 3, 4. So we can divide this matrix. So imagine now we have numbers here for all those probabilities. So we're going to call this first matrix here matrix Q. We're going to call this matrix matrix R. We're going to call this matrix something that is, we're going to do this one first. And we're going to do this one second, okay? So let's do this one first. Probability of going from an absorbing state to a transient state. Someone? 0, right? So this is what we're going to call this matrix. Now this one, probability of going from an absorbing state to an absorbing state. 1, right? But we have to be careful with, for example, can I go from 1 1 to 1 1? Yeah. Once I get here, I stay there. Remember the idea of an absorbing state is you get there, there's no going out of it. You're there forever. At least for that value, right? So yes, can I go from 1 1 to 1 2? No way, right? So I get 1, 2, 3 zeros. So you get the idea. I'm not going to be able to go from 1 2 to 1 1, so that's going to be a 0. It's going to be 1 0 0. So I have an identity matrix here. color? Just want to make sure I'm not writing with my nails. So, okay, so the bottom is easy, right? So stuff happens over here. So we can, and matrix Q is really one of the most important that we have to find. So transition probabilities from transient states to transient states. Transition probabilities from transient states to absorbing states. So we're going to still have a bunch of zeros here. So some of those transitions are not possible. Let's go ahead and think of, let's write here Q and R, just so you can remember what those names are. And I'm not going to have us go through everything. I want to be mindful of time. But let's speak, well, also the first one. Can I go from states, and when I say can I go from this to this, is after both engage in an attack. So however many dice they can throw at that point. Can I go from this state to that state? 2-1 to 2-1. We have several nodes. Okay, so it's going to be 0. Can I go from this state to that one?
Yes.
Yeah. It needs to happen for that to happen. So going from here to here, defense lost 1, right? And attack lost 0, which is possible because if the defense only has 1, the defense is only going to throw 1 dice, meaning that the attacker can lose at most 1 dice, meaning that the attacker could possibly lose none. So this is what happened from here to here. Attacker lost 9 and defense lost 1. So there is some number here. Is it possible to go from here to here? I see a few hands. Most of you are saying yes, and that's correct, right? This is the attacker will be 1. So we're going to have another number here. And going from 3-2 to 1, is that possible? Each one would have to lose 1. Is that possible? It's possible because now, so if you're going from 3-2 to 2-1, it means that each one of them, wait, can each one of them lose 1 dice?
Yes.
How would that happen?
Both roll 2.
So both roll 2 because now the defender has 2 dice, right? So if the defender has 2 dice, it's quite possible when you're comparing that the maximum of the attack won, but then the minimum of the attack lost. So it's possible here that each one loses 1 because the defender is now throwing 2. So there's going to be a number here. What happens over here? Are we going to have numbers over here? Possible. Can you see a transition here that is possible from these states to those ones? Can I have a show of hands for who thinks there are other numbers here?
Non-zero numbers?
No, 0 is a number. Is it all zeros? Yeah? A bunch of zeros here. So you see like how a lot of the states we can actually not get to them depending on where you start. We're going to have numbers here. And with R, similar things are going to happen. Some of them will have zeros. So just to, I'm going to go ahead and give away where we get numbers. So we get a number here. We get a number here. We get a number here. And then the last 2. what the transition probability matrix is going to look like for this Markov chain. Now this is for one particular type of attack. Can you imagine what would happen on that example 20 versus 10? How huge this probability matrix would be. But still, that is computationally more viable than simulating many attacks 1,000 or 1,000,000 times if you're doing Monte Carlo simulations. So it's still worth going down. Okay, so now the next step would be, what are those numbers? And going back to our bigger example, which is the 20 versus 10 example, if we can find all of these probabilities, because no matter how large your attacking and defending armies are, the attack can at most throw 3 dice, and the defense can at most throw 2 dice. Then knowing what happens here will help us find out what happens in the other ones, right? The transitions are going to be much bigger, the matrices, but the values in them are going to be repeats of those guys, right? So how many different ones we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have 9 different ones. And so if we can write and equal to R 0I, then we would like to go back to that question, which the original question, which was, what is the probability of conquering a territory when engaging an attack? So in other words, we are trying to ask, what is the probability that after an attacks, we end up in an absorbing state. So we are interested in that question, but we are actually interested in a particular outcome, which is to conquer a territory, right? So what we would need to do here is, so in Markov chains, you can calculate probabilities of, what is the probability of being in a certain, of transitioning from one state to the next after n such steps. And that can be done by multiplying this transition probability n times, right? So when you multiply this matrix by that matrix again, you are, now you're in the transition probabilities after 2 steps, right? So this is in the very beginning, when you have 3 versus 2. When you start engaging in attacks, let's say after 5, although you may not be able to go that far in this example, but thinking of your 20 versus 10, so after 5 attacks, can I construct such a transition probability matrix for going to the 6th step? And the answer is yes. You just have to multiply this matrix 5 times, and that will give you that same probability of going from step 5 to step 6. Okay. So when you're multiplying matrices that you can kind of subdivide into other matrices, you can actually just do the multiplication as if those were numbers. And so what you end up with, for example, is p squared equals this, and imagine having another one of that, right? So you have q squared plus 0. So you have q squared. And imagine having another one of these, so you have, for the second one, QR plus R. And then for the third one, you have a 0 again. Right? And for the last one, you have the identity again. Is this clear for everyone? And so you can keep on going induction, you can get to Pn equals Qn. And then this is going to look very much like a geometric series. So you're going to end up with Qn minus 1 times R plus Qn minus 2 times R all the way to QR plus R, which was the last one we had. And thinking of this part, so what was this part again? This matrix was the transition probabilities going from a transient state to an absorbing state, which is what we're really interested in knowing, right? After n steps, so after going, several times, what's the probability that finally we're going to be over with the work? Everybody looks forward to that. So we're really interested in looking at this part over here after n steps. And so we can simplify this that simplifies to that in a similar way that if you have a geometric series, you can have that closed form that looks like this. But in order for that to happen, we need to, this is the inverse of a matrix. We need to make sure that that inverse exists. So this is going to have to satisfy all those nice properties in order for inverses to exist. And this is really powerful because, of course, as n approaches infinity, okay? If we just think of, if this process would never end, of course, if you end up in an absorbing state at some point, you can still keep multiplying your matrix because all you're going to be doing is looking at the probabilities of going from absorbing state to absorbing state. So you can stay there forever. So it makes sense mathematically to think of n going to infinity, which means we're just staring at each other, not doing anything forever. So this is a very powerful result because no matter what kind of attack you engage in, 20 versus 10, 100 versus 104, it's going to be a huge matrix. You can set up the matrix, find what this is, and then in here, once you have what that matrix is, you can then look at, okay, let me look at the probabilities that I'm interested in knowing. So I want to show you one last example that summarizes, with numbers, what that's going to look like and how we can then get useful information. So I'm going to bring this back again. So this is a paper from someone that was looking to those transition probabilities, and they picked a nice example, so I want to use their example. So if we look at here, at this matrix, I minus Q inverse times R. So this would be, after you set up your transition probability matrix, you find what your Q is, what your R is, etc. And then you can calculate what that inverse is times another matrix, right? So it's just matrix algebra. You're doing operations with matrices. And so you end up with this transition probability, which we can read as, for example, what is the probability that after several steps, after you have exhausted your attacks, you go from state 4,3 to 2,0, which is an absorbing state. So the probability of going from here to here is 0.0754. The probability, and this would mean that the attack won, right? The probability of going from, by the way, this would be, this is the starting point. So in this example here, we're doing a 4-3. Okay, so this is, if this is what you're starting with, probability of going from here after you have exhausted the possibilities of attacks that you could have. Going from here to here is that, going from here to here is that. And of course, if you're trying to find out what is the probability of the attack, you're interested in knowing this, or this, or this, but not this, not this, not this. This is the attack losing. Yeah? Make sense? Right? This matrix here that we're looking at is the one that's behind here. It's after you have multiplied that matrix P several times, thinking about, attacking each other over and over again until you cannot possibly attack each other anymore, right? And going to infinity. So we are now this matrix looking at going from here straight to the end of the game. Not the end of the game, straight to the end of the battle. Okay, so in probability, if you have one or the other, right, you're adding up those probabilities. So if you add up all these probabilities, you end up with a 0.472. So the probability of conquering a territory, if this is how you're starting with, that probability is 0.47. So almost 50%. Okay? And so you've just answered that question, the magic question for this very small example, 4 versus 3. We're going to have bigger things happening during the game. So just to show you, but this is the game risk. So in the game war, what happens is we modified all of these probabilities to account for the possibility of the defense throwing 3 dice. Remember, that was the main difference between those two games. And so what's going to happen is it's going to make the defense even stronger. The defense already has the time among the dice. So it's going to make the defense even stronger. And so it's going to take a lot more armies from the attack to conquer that territory. And so just to compare some probabilities. Okay, so these are websites that have those probabilities calculated. This is just, Wikipedia for risk. You can look at what those probabilities are. So for example, if we have, look at the difference in color, which tries to emphasize, if you have the same number of attacking and defense armies, these are the probabilities. So you have, 2 versus 2, 3 versus 3, etc. So you usually have, oh, wait a moment, I think here, yeah, so this is slightly different than our example because our 4 versus 3 is their 3 versus 3 because they take 1 away. Okay. So, you look at that 47 for the example we just did. And so, for example, if you have a 4 versus 4, it's really their 3 versus 4. So, the edge of the green stuff is when you have the same number of attack and defending armies. And notice how that keeps in, in the beginning, I mean, it's quite big, but then you do have eventually increasing again, meaning that the attack always has the advantage if you have, the same number of attacking and defending armies. So in the game risk, having the same number, the strategy is just attack. You have the advantage, right? If you just keep holding, if you say, I'm going to save those to defend, and the other person has the same number, they're going to get your territory next time. But for the game war, that picture is much different. And sorry that I don't have the colors here. But if you try to look for, and that their matrix is similar to the one in Wikipedia, meaning that 7 is really 8 because they're taking 1 away. So if you look, for example, 4, which is really 5, and then look at 5, look how small that probability of conquering is. Right? And if you look at 8, which is really 7 versus 7, it's really small, it's like 20%. So if you have the same number of attacking and defending armies, the probability of conquering a territory is very small, and it just keeps on decreasing. So look at, for example, 29, which is really 28, and well, let's go up to 20. So 19. Ridiculous, right? 10%. Whereas in risk, it's like 60%. So, just to answer the question from the beginning of the talk, is a good, is a good offense the best defense? And for the game risk, yes. But for the game war, no way. If you play defense in the game war, you have a much bigger chance of keeping going for longer. I'm going to stop here, and I really would like to show you more probabilities, but this is what we can do with the time frame. Can I answer any questions?
So the war games last a lot longer than risk games?
Yes. So some war games, I mean, if you try to play mostly, it could easily go like 10 hours. I know that risk games can go long too, but usually any other questions?
In war, you still roll 3 as the attacker?
Yeah.
3 and 3
Yeah.
instead of 2 and 3.
One more question about the game rather than the math behind it. Is the math always been the same? Because over my lifetime, there have been about 30 countries that have emerged or not. Have they changed the territories on war or list?
Yeah, so both games have variations with different maps, but they also both have the same maps with just the only change in the dice. So yeah, the calculation, I mean, this calculation is don't really matter which map you're working with, but I know that there exists many maps.
But when the Soviet Union broke up, for example, did that change what territories they had to have and what used to be the Soviet Union, or did that not matter?
I don't think it matters. It just kept the same. But for example, I know that there's Star Wars maps. There's all sorts of maps like Game of Thrones.
Other questions? Let's thank the speaker.